Hi class, welcome to the second part of lecture for today. So the first half of lecture we were talking about life in extreme environments, and the motivation for that was the fact that we're going to start talking about looking for life elsewhere in the solar system. So what you can see in the background here is the planet Mars. This is a panorama from one of the rovers, and you can see the rocky desert that we encounter over most of Mars. Mars is a place that looks entirely Earth-like in many pictures, and if you've ever been to the American Southwest, to the painted deserts or the deserts in Nevada, places like this, this scenery does not look necessarily unfamiliar to you, which is one of the very alluring things about Mars, is there are times where it can look very Earth-like to us. Okay, so we're going to spend a whole week talking about Mars, probably close to a whole week talking about Mars as we go deeper into the term. In a couple weeks, we'll come back to Mars, but it's going to play an important role in our discussion here in this half of the lecture. So I wanted to put a picture up for you to look at, and we'll come back to Mars and discussion of Mars in just a minute. Okay, so let me do a couple slides. Okay, so this is also Mars. This is a slightly different area on Mars. This is very typical of the kinds of places that we're looking for when we look for life on Mars, and we'll come back to that. But you can see the terrain here. It doesn't look that different from terrain in Earth. It's evolved over the courses of Mars history, often by water. And that is one of the key things that we're using to look for life when we're on Mars. So keep this in mind, and we'll come back to Mars in a few days. But the reason we are talking about Mars is what I want to talk to you about today is a rock, a meteorite we found here on Earth called ALH 84001. Colloquially, it's known as the Allen Hills meteorite. There are many meteorites we found in the Allen Hills region, but this is the most famous one. So if you say the Allen Hills meteorite, most people are going to think you're talking about this one that I'm telling you about. We'll talk a little bit about tardigrades, which are something some of you may be familiar with, and then we're going to talk about everything as it relates to something called Panspermia. Okay, so that'll be this part of the segment. So the discussion here for this part is going to begin in Antarctica. So we've been talking about extreme life for the last half of the lecture, and certainly there are extreme forms of life and extreme adaptations of life in Antarctica. And we can talk a little bit about Antarctica, and we will later in the term when we talk about living in the ice. But today, the reason I want to talk about Antarctica is because it provides us an opportunity to find meteorites on Earth that come from other places in the solar system. Okay, so Antarctica is covered in deep sheets of ice. It is the only completely ice-covered continent around still today. The icing of Antarctica began building about 45.5 million years ago in the middle of the Eocene era. And you can see in this cross section of the continent here that most of the solid piece of the continent, what you and I would call the landscape, is currently buried under multiple kilometers of ice. And so over the last 45 million years, each snowfall has just been built on top of itself, and that ice slowly, the snow slowly compresses and becomes ice, and then it just builds up and it builds up and it builds up. So over time, there's about 26.5 million cubic kilometers of ice. That accounts for about 61% of all the fresh water on Earth. Okay. Now, what that means is that over almost all of Antarctica, there's not a single rock, right? Every rock in Antarctica, except near the shores, okay, so out near the edges there are the shores, or in the Transantarctic Mountains, which go through the middle of the continent there, there is not a rock to be found. Every rock on Antarctica has been buried for millions and millions and millions of years, okay? So when you're cruising around Antarctica, if you're walking around on the ice sheet and you see something like this, it looks a little weird. So what is this? Well, as it turns out, the Earth is constantly bombarded by meteorites. Many of them are big enough to land whole and intact on the Earth. Most of those that hit us are small, as we talked about last time. The smallest ones are the common ones. So a meteorite like this is, you know, kind of the size of your fist or a basketball or something like that. So this is one that landed in Antarctica. Maybe it was recently, maybe it was a while ago, who knows, but when it's near the surface, since it's darker, it absorbs heat from the sun that melts the ice around it. And then when you're standing there looking out across the Antarctica ice fields, they stand out very readily and you can easily find meteorites. So every season, the scientific organizations around the world mount expeditions. They send teams of people down to the Antarctic ice. They camp on the ice for a few weeks, and then they look for meteorites for the season. Okay, so one of the places where they've looked for meteorites in the past, and still do, is in the glaciers around an area off of the Antarctic mountains called the Allen Hills. Okay, and this is the most famous meteorite ever found in Antarctica. So this is ALH, Allen Hills, 1984 001. So it was the first meteorite they found in 1984 during the Allen Hills expedition to look for meteorites. Okay, so you can see there in the lower right, there's a cube for size. So that's a 1 centimeter by 1 centimeter by 1 centimeter cube. So this meteorite is, kind of a little bit bigger than a basketball, but you can basically hold it in your hands. It's heavy, it's a rock, of course. It has a kind of irregular shape. There are many things about it that tell us it's a meteorite, not the least of which is the very eroded round crust there that you see on the upper left edge. So that's what we call a fusion crust. It's caused by the very hot entry into the Earth's atmosphere, and that melts and fuses the material that the meteorites made into this crust around its outside edge. Okay, now there are lots of meteorites that we find in Antarctica. And one of the things that we do with meteorites is we study their composition. We're trying to understand, meteorites typically are left over from the primordial formation of the solar system, which we talked about a couple lectures ago. So we're trying to figure out what was the composition of everything that was in the solar system. But ones like this, we can look at their geology and their chemistry, and we can tell where they came from. So very often meteorites we can identify come from particular asteroids, from particular planets, or particular moons in the solar system. And so one way you do that is you look at the geology. Another way you do that is that if you can cut into objects like this, often there are enclosed pockets which trap gases from wherever the meteorite originated. And in this particular one, we can tell that this one came from Mars. Okay, so its geology looks just like the geology that we find on the surface of Mars. Trapped gases have the same signatures as the Martian atmosphere. Okay, now that is not why this meteorite is famous. We have plenty of meteorites that came from Mars. Okay, but this one's famous because in 1996, a team of scientists were looking at cross sections of the Allen Hills meteorite, and they found these microstructures. Okay, that microstructure right there in the middle looks seductively like an Earth microbe. It is elongated, it is segmented, not unlike microbes that we see on Earth. It's about the same size, okay, except it's fossilized. And so the idea, the supposition, is this came from Mars. This structure, whatever it is a fossilized structure. And so maybe it's a fossilized Martian microbe from the ancient history of Mars. Okay, that would be remarkable if it was. It would be the first evidence of life from somewhere else on the in the solar system. Okay, now extraordinary claims require extraordinary evidence, but this is pretty extraordinary. And in this paper, which if you're logged in with your Northwestern credentials through the VPN, you should be able to get it through the library, through the electronic journals if you're interested in reading it. But this paper kind of laid out the case for these possibly being that. Okay, now it's not just the structures, right? The structures look very much like what you and I might expect microbes to look like, okay? But there are other lines of evidence that the team points to that they think are highly suggestive that this might be of organic origin. Not the least of which is when you look in the area around these structures, you see the chemical products that on Earth would absolutely 100% be taken to be biosignatures, okay? So in particular, when you have your normal life processes, you produce byproducts, either from building your body or as waste products. Those typically show up geologically as carbonates, and in many places in carbonates, you'll see high concentrations of something called magnetite. They definitely see that in the Allen Hills meteorite. Another example is you will see very complex hydrocarbons. So there's a class of hydrocarbons that we'll talk about a little bit later in the quarter called polyaromatic hydrocarbons. So those are PAHs. They're complex, long chain hydrocarbons, and they see those in the meteorite as well. Okay. Now, taken at face value, none of these things are absolute indicators of life, right? We see magnetite in inorganic environments all over the place. We can geochemically make elongated structures like this. We see polyaromatic hydrocarbons in non-life-bearing environments, okay? And so critics of the idea that this might be fossilized life point to those ways that all of these signatures could appear in the absence of life. But if you are in favor of the idea that there might be life elsewhere, these are all things that if you saw it here on Earth, you absolutely would say, yeah, that's a sign that we've encountered life. So we find ourselves, we talked very early on about cognitive dissonance. And so we very much find ourselves in that situation, particularly with the Allan Hills meteorite, because we on the one hand see things that would convince us it was life, it was in a normal situation here on Earth, but because it's from somewhere else in the solar system, it causes us to doubt what those things are actually telling us. So for critics of this idea, what it really boils down to is, are there other geologic processes that can leave the traces that we're talking about and fool us into thinking that this is a signature for life? Okay. Okay, now why are we talking about this? Okay, well, let me remind you of a life form that many of you have probably heard of. These are called tardigrades. Okay, so tardigrades also go by the name water bears or moss pigs. They are small, eight-legged microanimals that you can see in microscopes. These are electron micrographs to show you the kind of extreme detail of the tardigrades. The reason they're so famous is because they are life forms that are just really, really resilient against constant changes in their environment. They can survive extreme pressure, they can survive in the vacuum of space, they can survive high radiation environments, they can go through long periods of time without food and water. They're just very, very resilient against changes in their environment, which is a survivability trait. Okay, and so we find these all over the Earth. We find them from the highest trenches, highest peaks of mountains to swamps and trenches and canyons all over the world. Okay, so tardigrades are a very resilient form of life. Now, I just told you that the Allan Hills meteorite came from Mars. How did that happen? Well, you have your solar system here, right? You got the Earth over there on the right, you got Mars over there on the left, and possibly with some small form of bacterial life. That's the little green widget I drew there, okay? And you have some meteorite that's flying through the Earth, and it comes in and it impacts Mars. And when it does that, it causes a gigantic catastrophe on Mars. It digs a big crater in the ground, and it throws material up. Some of that material will, as we say, have escape velocity and will go out into the solar system, and it could fly across the solar system and eventually arrive at Earth. That's how the Allan Hills meteorite got to us, okay? So if there are extreme forms of life, like the tardigrade, that can survive in outer space, like the tardigrade, then there's this interesting question, which is, if meteorites can certainly travel from one planet to the other, as the Allan Hills meteorite has, then maybe they not only could carry evidence of life from wherever they came from, like the microfossil structures, the microfossil-like structures, the possible microfossils that we see in the Allan Hills meteorite. Not only could they carry traces of life, maybe they could carry life itself, like a tardigrade, from one planet to the other. And if that happens, that's what we call panspermia. That is the transfer of life from one body in the solar system to another body in the solar system. And there are many examples of that in science fiction, right? That's kind of what most science fiction horror movies about life coming to Earth are often about, unless they're invasion stories like The War of the Worlds. But it's not an unreasonable idea. We certainly see meteorites come from one place to the other, and we certainly see life that can survive the journey. Okay, but it begs an interesting question that we have to seriously concern ourselves with if we're going to think about life in the solar system. And that question is this: where did life start and come from? We see life on Earth, and we've been operating under the assumption that it started here on Earth. But the idea that panspermia can happen and the evidence that that objects do transfer from one planet to the other, and the knowledge that life forms exist that could survive the trip, beg the question we must consider that maybe life started elsewhere in the solar system and came to Earth and was simply able to survive on Earth better than it survived elsewhere. Maybe we're still going to find it elsewhere in the solar system. Equally likely, when we start looking for life elsewhere in the solar system, we're going to have to ask, did we put the life there, bringing it on our spaceships, or did the life somehow transfer to that world from Earth in much the same way that we're talking about the panspermia here? Okay, so that's the little bit of food for thought for you for the weekend. Think a little bit about that. We'll talk about panspermia a little bit more when we talk about looking for life elsewhere in the solar system. I hope you all have a great weekend, and we'll start talking about other worlds on Monday. Okay, so take care, everybody, and we'll talk to you soon. Bye-bye.